In the last video, we looked at how to find limits algebraically. We're going to continue to do that in this video, but we're going to look at some more interesting cases. We're going to look at what happens when a limit goes to infinity, or when we let the x go to infinity and we can find a limit. Now, these bring about some very specific things. What these actually are showing us is that we have an asymptote in our equation. Now, back in pre-calculus, we learned how to find asymptotes. We found vertical asymptotes, horizontal asymptotes, slant or oblique asymptotes, but we gave a very hand-wavy, vague definition. Probably received a definition something along the lines of an asymptote is an imaginary line that we approach. Hopefully you were not told that it was something that you couldn't touch, because horizontal asymptotes we can of course cross a horizontal asymptote. But that is a very vague, non-specific definition, so we're going to tie that down in calculus. We're going to be able to really understand what an asymptote is. Now, if your teacher was doing a good job back in pre-calculus, they probably told you that an asymptote was a limit, and that's exactly what it is. And to define this very formally, a line x is equal to a is a vertical asymptote of a graph if the function, if either statement is true of the function, the limit as x goes to a from the left is equal to plus or minus infinity, or if x is going to a from the right, that limit is equal to plus or minus infinity. So we actually have 4 different cases that can set up a vertical asymptote, and one of the 4 has to be true. If we approach a from the left, or if we approach a from the right, and then if either of those lead to a positive infinity or a negative infinity, it doesn't have to be that we have both things true. So it could be that only one thing is going to infinity. From the other side, it might not exist, or it might not go to infinity at all, and that would still be an asymptote. So either or gives us a vertical asymptote, which means proving something is a vertical asymptote is much easier to do than proving something is not. To prove something is not an asymptote, we have to disprove both cases, versus if we want to show it is an asymptote, we just have to find one or the other is true. If we want to find a horizontal asymptote, then a line y equals b is a horizontal asymptote of the graph of a function if either the limit as x heads to infinity of f of x is equal to b, or the limit as x heads to negative infinity of f of x is equal to b. Again, an or statement. It does not have to be that one side is going to that set value and the other side is going off to infinity. If one or the other is going to that set value, then we have a horizontal asymptote. And the b is just indicating some set value. B is saying it can't be going off to infinity. So just quickly to give you an idea of what would not work, if we look at the limit of this function as our x heads to infinity, our y is also heading to infinity, that is not that set value. Therefore, we don't have a horizontal asymptote. So let's look at these things algebraically. Let's look at them using their equation. So let's start off really easy. Let's take 3 over x minus 2. Now, from pre-calculus algebra, you learned a lot of rules for determining when we have a horizontal or a vertical asymptote. What I want you to do right now is forget all of those, or at the very least, never use them again to tell me something is or is not an asymptote. We want to use our definitions for the asymptotes using those limits. So let's start with a vertical asymptote. Now I say forget it, but we're going to use a little bit of our previous knowledge. If we look at this, we know that 2 is not in our domain. 2 is not in our domain. We know from before it's an asymptote, but we got to show that. We can't say, hey, we set the denominator equal to 0, we find 2, therefore it's an asymptote. No, we got to go a step further. We do know that we can't have the denominator being equal to 2. It's a domain restriction. So let's see what happens when we take the limit as x heads to 2. Now, I don't have to put coming from the left or the right, but remember, with that definition, either or works. And it could be that they're headed 2 different places, and if they're headed 2 different places, what we're going to say about this thing right here is that it doesn't actually exist, and that's not helpful. So I might as well pick one or the other, and because this one I know that both sides is going to approach one of the infinities, it doesn't really matter, but I'm put a little negative on there, just because I know it's going to work, right? So let's find the limit as x heads to 2 from the left of 3 over x minus 2. So if I just plug in that 2, we see that we get 0 in the denominator. And let's think about really what that limit is telling us. And I'm going to do this kind of off to the side, a little bit of scratch work here. If our denominator is getting really, really close to 0, so we have 3 over, I'm going to start with something a little further over from 0, 3 over 1. Then I get a little bit closer to 0, 3 over 1/10. Then I'm going to have 3 over 1 over 100. And it's just going to keep progressing. It's going to get closer and closer to 0 because remember, we don't actually care about what happens at 2. That's not the point of a limit. We want to see where we're going with this thing. So we're getting closer and closer to 0 in the denominator, but we're never actually getting there. We're getting closer and closer. So if we think about what each of these things equals, this would give us 3, this would give us 30, 300, 3,000, and we see these numbers are going up and up and up. They are approaching infinity. So this thing is going to one of the infinities. Now it's very imprecise when I set this up because I wanted to give us a general idea and not figure out which of the infinities is going to. I was going to 2 from the left, meaning I have values a little bit smaller than 2. So, start with 1. This would have actually been here a negative 1. Then if we had the 1 and 9/10, this would have been negative 1/10. Then we would have had a negative 1 over 100. All of these would have been negatives, which just means we have negatives here. So really, we're not going to positive infinity. We're going in the complete opposite direction. We are going to negative infinity. So our answer for this is negative infinity. Whenever we find a limit has a 0 in the denominator, we are going to one of the infinities. The key is to figure out which one we are going to. And so because that 2, we're subtracting something bigger from it because we're not actually getting to 2, we're coming at it from the left. That will give us a negative infinity. So the case where if we have a negative on top of that number, it's always going to go to the negative infinity. That is absolutely not true. If we had just switched these two numbers and added 2 minus x, then we would have been going to the positive infinity. So it helps just to think about some values immediately around those numbers. So right away here, what we've already shown is that we do have a vertical asymptote. At this point, we can state with confidence we have a vertical asymptote at x is equal to 2 because we found the limit as x approaches 2 from the left of our function equals negative infinity. I do expect this level of reasoning to explain why we have an asymptote. We have to state we've found that limit, we found that it went to negative infinity. We don't have to show the other side, right? At this point, we have shown it. That's why I always say it's much easier to show the existence of rather than the proving of non-existence. We've shown that that vertical asymptote does exist, but sometimes it is helpful for our graph, especially as these rational functions get more complex, to find both. So just for the practice of it, let's find the limit as we approach 2 from the right. And so we're going to be looking at the limit as x goes to 2 from the right of the same function, the 3 over x minus 2. So same idea as before, we would be at 0 in the denominator if we were at 2, but the thing is we want to approach 2, so we can use our same little reasoning as we did before. Now if we start pretty far away from 2, start at 1, we get a 1 there, but this time it really is a positive, so ignore all the red signs. If we get a little bit closer, 1 and 9/10, and we have 1/10 left over, again it's going to be the positive in this case, and we're going to have the positive 1 over 100, then the positive 1 over 1,000. So in this case, all the numbers are going to the positives. We do get a positive infinity. And so this, again, would show us that we have a vertical asymptote. If this hadn't been infinity, it doesn't mean it's not. It just means it only worked from one side. So we're getting a pretty good indication now on the graph as we approach 2. If we're doing so, we know this is an asymptote. If we're doing so from the left, we know that we're going down to negative infinity. If we are doing so from the right, we know we're going up to infinity. Now this is a rough ballpark because I don't know where my horizontal asymptote is yet. So let's find that horizontal asymptote next. Now this one, I'm not going to make any assumptions on knowledge first. I'm just going to jump right into the definition. And so the definition says we need to find the limit as x goes to infinity. And so we are looking at the same function. And we have the 3 over x minus 2. And so now we have infinity in the bottom, and it's not super clean, but we can think about it in the same way we did the last pattern. So just off to the side, let me write down some numbers. We'd have 3 over, let's say we chose 10 at first, so we'd have 3/8. Then I choose 100, 3 over 98. Then I choose 1,000, so we'd have 3 over 998. The numerator is always staying the same, but the denominator is getting huge. And so what these numbers are going to, they're approaching 0. So what that tells me about my limit is that it is also approaching 0. And so as per the definition of a horizontal asymptote, we now know we have a horizontal asymptote at y equals 0 because the limit as x goes to infinity of f of x is equal to 0. We found a set value for that limit, and so it has to be a horizontal asymptote. If this one hadn't worked out, we would have also had to have shown the negative case because it's much harder to disprove something exists than it is to prove it does exist. So because we found it right away that it did work out, we now know for certain that we have that horizontal asymptote. So let's put this together with our previous knowledge. We know we have this horizontal asymptote on the x-axis. We knew we had a vertical at 2. I knew that the end was going up at 2. And we did say at infinity, as x goes to infinity is approaching 0. I don't necessarily know from the other side. Now, what we know about rational functions is that it is. I know this part's going down, but I don't really know what this end is doing yet, so it might not be a bad idea, just for our own sake, to find that limit as x goes to negative infinity, especially as the functions get more complex. And so we have the 3 over x minus 2. Well, guess what? Even if we're going to negative infinity, this is still going to a huge number. 3 over a huge number is still getting really close to 0. And so in this case, yes, rational functions, we do approach that asymptote going both to positive and negative infinity. We know that about rational functions. So we've just shown that we have vertical and horizontal asymptotes. Let's take that linear function that I talked about in the beginning, and let's show that that one does not have a horizontal asymptote. So let's take f of x is equal to 2x plus 3. Now, to disprove the vertical asymptotes, we would have to be given a point, right? How could I show that there's no vertical asymptote at, say, 2? Well, if we plug in 2, we see that we get 7 coming from both left and right. Not very interesting, not a vertical asymptote, but I want to concentrate more on the horizontals because they are always, if we have no domain restrictions, we always know we're not going to have a vertical, but the horizontals we can still have. So let's look at the limit as x goes to infinity of 2x plus 3. So if we plug in that infinity, obviously we have 2 times infinity plus 3 is still going to infinity. That's not a set number. So far, we don't have an asymptote. We can't say that there's not a horizontal asymptote because I do have to show both directions. And I don't parentheses. So this time we have 2 times negative infinity. That's going to negative infinity. Add 3, it's a rounding error. It's still negative infinity. And so we see that both to positive and negative infinity, we're going to infinity and negative infinity. Therefore, we do not have a horizontal asymptote because the limit as x goes to positive and negative infinity of our function is equal to infinity or negative infinity, not a set value. So again, this would be the level of reasoning I want to see for disproving or for showing that we don't have a horizontal asymptote. Let's show we don't have a vertical asymptote on something that we might think would have one. Let's take x squared minus 3x minus 4 over, let's do x plus 1. So if we look at this, we'd say, well, it looks like there might be a vertical asymptote at x is equal to -1 because that would be our domain restriction. So putting a question mark there because I haven't proven anything yet, I haven't shown anything. I'm kind of making an assumption. It might very well be wrong. So to test this, we have got to look at the limit as x heads to that -1. Now before, I went ahead and put a negative plus or minus on that -1 to show that either way was true, and we can still do that. If I put that negative up there and I find that I get a limit value, it's not just infinity or negative infinity, I've also got to show the other one. So sometimes it's a better idea, if we know something is not going to have that limit of negative or positive infinity, it's a better idea to hold that sign off of it, because then we disprove both cases in one. I created this problem so I knew that it didn't have a limit of infinity or negative infinity, but we could very quickly see this by factoring. If I factor that numerator, I'd have x minus 4 and x plus 1. And of course the denominator already its own factor, so we have the x plus 1. Now we know how fractions simplify. We can cancel out those 1's. And we'd be left with an x minus 4. And now this is just a polynomial, and I know I can plug directly in for that -1, so we'd have -1 minus 4, and that would be equal to a -5. And so what we've just shown is that we don't have a limit going to infinity or negative infinity, and the limit is 5. So we can state with confidence now, there is not a vertical asymptote at -1 at x is equal to -1. And to finish out this idea, we can state what it is. There is a hole. And this ties back into our knowledge of 171. We said if ever the factors match on top and bottom, that would give a hole instead of a vertical asymptote. We've now defined the vertical asymptote to say, hey, if it's going to infinity or negative infinity, it is a vertical asymptote. So the second we see that it does not, we know that it's a hole because in terms of domain, this function still has that domain restriction that x can't be equal to -1. So if I were to ask you for what is f of -1, we'd still have to say it does not exist. But now we've defined it a little bit further. We know that it's a hole because we know exactly what it approaches. So that's useful when we go to do its graph. I'm going to take some shortcuts here. I know what this thing will look like. It's just a line x minus 4. So ballpark, I should be going through the -4, not the -3. But that would be a ballpark of what it looks like, but it's not just a line. It's not just what this thing simplified to because we knew that it didn't exist at the -1. So at -1, we can now come in and be a little bit more precise. I know that that -1 is going to have a hole there. Make that a little clearer. -1 has a hole, and its y value is -5. I know exactly what the y value would have been had we actually not had that hole there. So let me try and actually go through the hole. There we go. And so that would be the graph of our function. It should be a straight line just with that hole at -5. Now, if I had chosen at the very beginning to put that little negative on the -1 or the positive, it doesn't matter which one, I would have twice as much work to do because I have to show both cases not going to infinity or negative infinity. So I would have done all this work and I would have done it all again with the other case, which is why I think sometimes it's easier to leave it off, especially if you know it's not going to have that vertical asymptote. Now, it seems like in all these cases, it doesn't matter, right? If it has it coming from one side, it has it coming from the other side, or if it's going to a point on one side, it's going to a point on the other side. So when might we see that we have something like a vertical asymptote or horizontal asymptote on just one side? Well, let's take the function g of x is equal to 2 to the x. And we should remember from pre-calculus that exponential functions do have asymptotes. And so it's not going to have a vertical because there are still no domain restrictions. It will have a horizontal, however. Remember, we can find those horizontals by taking the limit as x goes to positive or negative infinity. And here's where your previous knowledge can speed you up a little bit. I were to look at the limit as x goes to infinity, I wouldn't find this asymptote right away. Because if I raise 2 to really large powers, so again, you can write out some numbers if it helps you see where it's going. But, if we have 2 to the first, that's going to be 2. 2 to the second is going to be 4. 2 to the 100th is a really huge number. We can see that as these things go up and up and up, we are going to infinity. And so our limit here would be infinity, and we'd have to say, hey, there's no horizontal asymptote, but we can't say that because remember we have to check both directions. So I'm also going to look at the limit as x goes to negative infinity. So if we think about this one now, we'd have 2 to the negative 1, 2 to the negative 2, 2 to the negative 3. Just keep going up. So we would really have 1 over 2, 1 over 4, 1 over 8. And we can see that the denominator is growing more and more and more. And that is going to 0. This thing is approaching this time 0. Remember, anytime that denominator is growing while the numerator stays the same, it is going to 0. And so now we see that on this one limit, it is showing us that we have that horizontal asymptote. There is a horizontal asymptote at y is equal to 0 because the limit as x goes to negative infinity of our function g of x is equal to 0. And that was only true going to negative infinity, not the positive. And so this is a good example where we can have a horizontal asymptote even though only half of the statements are true, right? We only needed one or the other as an or statement, not an and. If we think about a function that has a vertical asymptote coming from one side, not the other, we could take the log base 2 of x. I'll call this function h of x just for a little variety. I know that log is undefined at 0 and anywhere to the left of 0, so it has domain restrictions. Of course, if if we look at something like the limit as x goes to negative 5, well, nothing exists on either side. But because the domain of the log starts at 0, not included, and goes to infinity, it might be useful to look at the limit at 0. So if we look at 0, and because it only exists to the right, I only have to look from the right of our log base 2 of x. And if we think about what this would be, that thing is going down to negative infinity because of the way that logs work. And so here we see that we have a vertical asymptote at x is equal to 0. Even though the limit wouldn't have existed coming from the left of 0, we only need one or the other. And so we've shown that we have our vertical asymptote because the limit as x goes to 0 from the right of our function h of x is equal to negative infinity. So we only have to show one or the other is true to show the existence of an asymptote. To show that there is not an asymptote, we have to show that all cases are not going to work out. But we do want to make sure that from here on out, we are using our very precise definitions of asymptotes, not just looser definitions. Now, the slants, that would be the one that we haven't really talked about. Slants are still kind of defined in the same way. If we see that the degree of the numerator is 1 larger than the degree of the denominator, that would give us a slant asymptote. So because that is not really any different than our previous definition, I'm not going to show any examples with those. You can find other examples in the book and the notes.